forms in dense gas and dust cloud, and then like something like the star forming areas of pillars of creation. And I will try to take your focus to the STD here, spectral energy distribution. Keep an eye on it. And slowly, as time goes by, there is a core collapse of the star, and with this collapse, there is huge filaments coming out, and still there is not much. There is a cold black body. We don't see enough here in the SED. And slowly, in a million years, we start seeing a star, but from the gas and from the envelope, there is also a disk around it. And when because of conservation of angular momentum, and here is what we call class 1. This is important, the nomenclature. The infrared axis, which you are seeing compared to the star and the disk, is much higher. And that is one type, a very early protoplanetary disk. And slowly, when time goes by, when more planets, grain growth happens, we believe that the grain growth of planet formation already starts at class 1 stage. And slowly, this millimeter size objects becomes kilometer size, and gravitation takes over and forms planetesimals. And this is PDF 70 here. This is a real image taken by composite image of ALMA and VLT observations, and you can see multiple planets in formation here. These are still forming, so there is a core and a disk around the planet as well, and the primary planet forming disk as well is still there. So what we believe is planets are forming, and slowly the dust and gas is collected due to this planet formation. There is I think recording. So. Yes, this meeting is being recorded. Okay, yes. Okay. Then. Okay. So as and when planet formation starts, the gas and dust are swept away by this planet formation. The accretion of material keeps on happening. And slowly the infrared axis, which we saw before, it starts reducing. The slopes become more negative and negative. And you can see that the infrared axis is reducing and the envelope is completely dissipated. There is no outflow or interactions with the ISM. And this is the class 2 stage where we expect to see the remnants of planet formation. So there is more aggregate objects here, like planetesimal size objects.
These are all the star spots. When they get star dies after that.
Yes, after that, when the star formation, after the star formation.
What kind of star is it? Massive star or any star?
Basically, we are like with direct observation with millimeter, we are seeing A type, B type massive star. We are more privy to looking at those kind of stars because of observational bias. But this happens with even with solar type of stars. This is what, for example, I will show the disk like later when the disk slowly dissipates. This is a system HR8799 where the planets are moving. Here, this is around an A-type star. But for example, our Kuiper belt is also a remnant disk. So the Kuiper belt is something similar to a debris disk. So yeah, so that's what we believe that it happens to even low mass stars as well.
No, but it has to surround a star, but if that star is gone, then
no, it's not after go. It's the formation of
the beginning of the formation. It's with star formation. So while the star is forming, the star is also evolving. The envelope around the star is slowly, the material is raining down onto the planet forming disk. So yeah, and with class 3, which is the debris disk, which is similar to the Kuiper belt, the planets have already formed. In this system, there's a very far separated disk in the system as well, very similar to the Kuiper belt we see. So yeah, so these are the 3 classification, class 1, 2, and 3, which is the SED classes of protoplanetary disks or planet forming disks. So as I said, this planet form, like this this system was a benchmark system for high contrast imaging for direct observations. And when we saw that multiple planets are moving in the 2:4, the ratio which our Venus, Earth, Mars have the same ratio, or Jupiter, Saturn, Uranus has the same separation ratio. So although much far apart, and we also believe that this system, what we are seeing with direct imaging, I also talk about direct imaging here because that is what is the state of art right now, not just transits and radial velocity, because the indirect method of observation, we see very close planets like hot Jupiters. Because you can imagine, like, if we want to see a transiting event, then the transiting planet has to be very close to make a difference in the light curve. So that's why we are only looking at hot Jupiters. But if we want to see something similar to solar system or something far separated, we have to look at direct imaging. So that is why this was a benchmark observation by direct imaging. And here we understood, the idea is what is the forming mechanism between what is separating the hot Jupiter formation and this kind of planet or solar system type of planet. What is the mechanism that is changing? So what the idea, one of the biggest idea theories which we are believing is a radial drift. So there is the planets form at one place, and slowly due to gas drag, due to tidal disruption, there is a drag and the planets move closer. And all this is happening while the disk is still intact. So in class 1, class 2 stage. So the planets are moving, and so there is a balance between a radial drift and a gravity and the angular momentum. So everything takes place, and this is why this is something which we understood with multiple direct imaging observation. This observation is this is a composite of VLT, Gemini, all the high contrast images. Yeah.
This is the observation of type 3.
Yeah, system.
Type 3.
Yeah, class 3.
And if I understand correctly, there are 3 planets.
There are 4 planets. This one, this, and this. These 4 planets. The central star is Mars, just for coronagraphic observation. Yeah.
And do you have any information regarding this kind of Mars of the planet?
These are all I can show. These are all in these areas, because these I think there are these few systems. One of these are HR87. These 4 planets, very high orbital period, very massive, like Jupiter, Mars, planet. So planet, but not brown dwarf. So
high mass, but lower.
No, high mass, high period, very far, very. So this is, so the problem of each of this observation. So now we know there are like 5,000 known planets. So this plot is done 2 days before, so last week. Yeah. So there are about 5,000 planets, more than 5,000 now. Most of them you can see it's observed by radial velocity and transits, or discovered by these 2 techniques, which has been very successful. But we can see it's very biased to this region. What we need, these are solar system planets. This part we are looking at, we don't even have enough observation for like exo, Uranus and Neptune. So these planets are also very important, because theories also suggest that the formation of giant planets were the reason because of which rocky planets form, because it makes a potential barrier, and that's when rocky planets are more easily formed. So, and this is what we are looking at in new observations as well. I'll tell you about this. But we are not seeing this right now, and this is only right now, this area can only be filled by micro lensing, which is also again a difficult process, because it's similar to gravitational lensing, and it needs a lensing event. So it's very difficult to get observations at this area. Direct imaging means this kind of planets, because that's the limit of observation because of optics. It's direct imaging needs, we have 4-meter plus telescopes are the biggest telescopes right now. TMT will hopefully get us down to this limit. But yeah, realistically, it's very hard.
Those are still gas giants or gas.
Yeah, gas giants.
Yeah.
Of course, Jupiter-sized gas giants, like massive gas giants.
Star.
These are with direct imaging. These are not close to the star.
But the image seems to be less than 10 AU. No.
No. This is
That one,
Mhm.
pretty close to that mark. So one of them is like 15 AU. 15 AU is not close.
15 AU is
Jupiter is far closer than 15 AU.
yeah.
Pluto is 40 AU.
Yeah, I think
Yeah.
yeah.
Correct.
So yeah, so now we have some idea, some background, and some recollection of what we have till now. So let's jump into observation right now. With radio observation, although optical is very good, we are looking at water absorption band, silicate feature, and all that, but we need radio. It's very easy because the atmospheric noise is much less in this region. But obviously, we have the size issue. So the angular resolution problem, most of us are we know, because with optical telescope, we get like 3 arc-second resolution with 5 millimeter. But with radio telescope, even with 70-meter diameter, we get only 1.5 arc-minute. So we need really big radio telescope to get the resolution we want. If you want a single dish radio telescope, just for a benchmark, I just want to say that human eye has 20 arc-second resolution. Oops. Yeah, 20 arc-second resolution is what we see with normal eye. So if I don't know how many of you know about this event. It was in early 80s or mid 80s. So Green Bank made a telescope, a huge telescope. You can see the cards here for reference. And the next day it broke apart. Like there were billions of dollars, billions of pounds invested, and one day it just broke apart. So because of the size and the weight. So of course, interferometry to the rescue. Remembering Young's double slit experiment and interference pattern, I just want to tell that what we observe, this is taking time. What we observe by radio interferometry are fringes. It's not points which I showed before. It's not like looking at, oh, there is nice planets I can see. So there goes a lot between what the detector is observing and then the mathematics behind it, and then getting back to what we are. So these are ALMA telescopes at working. There are about when I didn't know that many of these antennas and move because we have to set array, observe certain.
Central
No. It's just multiple antennas. Yeah.
But the density are not the same in all the time.
Yeah.
So there are you want
Spread
to
over.
use the largest arm, but then
Yeah.
in some places you want to have many dishes to have more better properties.
Resolution and sensitivity. So just now the slits are not just two, there are like multiple slits. So the interference pattern is all crazy. It's much more harder, you can imagine. So what happens? Just a very short idea. So as Sir was telling about the kind of observation we are doing, what kind of arm we put the antenna there. So say there are like 20 small antennas, 20 antennas we want to collect at small area. So like we are just packing it densely within a small area. And the observation we are making is of this galaxy. So what we get after all the data reduction is something like that. We will get something like the output image. And this is like 10-minute observation. Then the same input. We increase the number of antennas are the same, but we change the configuration. So we make it in a large Y. Then we get something similar but not good enough in signal to noise. So you can already see the difference. We keep the same 10 minutes time. Now we increase the number of antennas. We make it 50, and then you can see how much it is improving. Again, it's same configuration, just number of antennas have increased. And now the time has increased. We are making a 60-minute observation, and we see much better resolution. So the observation is a combination of the number of antennas, the configuration. It makes a lot of difference if we make like a circular configuration or a Y configuration. There are limitations of configuration. You can't just make a shape like your face. You can't just do that. There are certain sometimes while you are applying for observing time, they only give certain just these. There are only this time we will only observe in these configuration. That's it. So
there are spare antennas there, so it would
no, but not very important. So if you remember the black hole observation, the whole globe was an interferometer. So what happened? We also take into account when Earth with the rotation, and therefore the increase of time, we also are increasing the number of points. So that's how we also increase the resolution and sensitivity. So it's a complex process, and this is not just, I want to tell you that when we are observing in sky, and what happens in the detector, we see in a Fourier plane. So from that Fourier plane, we have to inverse Fourier transform to get the image. So again, while we are doing an inverse Fourier transform, so when we are doing a data reduction, we have to take certain models. So there are a lot of limitations. So that's the underlying idea. But still, with all this problems, all this long process, why still ALMA has been very successful, particularly for protoplanetary disk planet forming observation. There are a lot of people doing galaxies, and yes, but majority, if you see any ALMA conference, 70% of the conference time will be given to planets and protoplanetary disk people. That is because of what with radio, what we are looking at, what part of the disk we are looking at. So what sub-millimeter, we are mainly looking in this region, the sub-millimeter. So ICES are very important because we look at what is happening with Neptune, Uranus, so how these are forming, and this potential barrier, which would be important for rocky planet formation. All the solid aggregate, if we look at the disk midplane, we are previously looking at this area. With no other observation type, we can look into this area. And that's the part where solids are forming. And so if we know the mass of this solid in the initial stage, we can tell what kind of planet it will form, obviously by evolutionary models and everything. But with more and more observation, these models will also be refined. And with if we do a chemical observation, like we do grain chemistry, we study the grain chemistry. If there's silicates, carbonaceous, we can say a lot about planet formation. If there we can find like biosignatures. So a lot can be said. And that's where we are going forward. And now let's the beginning of pretty images again. So with ALMA, with the ODISEA, this is the Ophiuchus star forming region. And previous observation, we saw a multitude of different types of disks with a lot of substructures. I want to again recall that having substructures means that there might have been planet formation which have created gaps, and those cavities, central cavities and certain gaps, and there can be like some spiral arms. there is some interaction between planet and disk, or binaries and the disk. So yeah, we have seen like different classification, like this is class 1, this is again class 1, this is more evolved form of this, multiple types of different substructures here. But one thing was, we were looking at massive disks before, because when observations happened, in the beginning, we wanted to do what we know. So we knew about this disk from the spectral energy distribution, that there can be nice structures, and we looked at massive disks. So it's easy for observation. So when I talk about massive disks, it's about more than 20 millijansky, the flux.
What is the thickness of this? This is the planet formation disk.
Yes, so horizontal thickness, it's no, 1 parsec, I don't think so. It's much smaller than that. It's not where, like, it's
So
millions of
the radius of the disk, or the actual
horizontal depth of the disk.
thickness would be, yeah, because the radius itself is like what, 100 AU
Yeah,
or something
100.
like that.
It's
So
it's not
the
similar to the
thickness is-
galactic disk. It's not, yeah.
yeah. So
Just-
the
just to
thickness
keep-
would be maybe 100
Few-
of that, or
Yeah.
something like.
They are almost coplanar.
That's right. Yeah,
If-
I mean, even in solar system, only one planet is like.
Yeah, coplanar. And also when we talk about the varied eccentricity and how the planets we are seeing, if they are very different in coplanarity, we can discuss a lot about if there has been interaction with, or it can be a flyby, there have been a flyby or something like that. These kind of studies are also being done continuously and being evolved. So ODISEA actually is the largest, I would say, complete ALMA disk survey in the closed star forming region. So within like 140 parsec, and there are total 300 targets. But when we look at the 4 millijansky to like 30-40 millijansky limit of flux, then we have about 100 disks. So right now we are looking at 100 disks, which is also not a small sample. And majorly it's divided between class 1 and class 2. We are not looking at class 3 observation, because class 3 becomes very thin, because the gas has been completely dissipated there. So when class 3, and then it's very hard to observe with ALMA. So yeah, so the goal right now with the new series of papers is to understand obviously the disk demography and their correlation with SED class, and studying the new substructure. We are seeing a lot of new substructure which we had not seen. We are seeing a lot of new binaries, their formation, and how they are changing with different with their age.
The target is only single galaxy or different galaxy?
No, just a single galaxy.
Yeah.
One thing I would like to stress again, I should have done that, is we are with protoplanetary, like this, when we talk about planets, exoplanets, there has been only one observation outside of galaxy. One exoplanet known outside of galaxy, that too was a microlensing event. So it's not possible to re-observe and confirm. So yeah, so this is our sample size, but you don't have to we have a lot of resolution, but just for this talk, we are focusing on the this frequency 410, and there are, as I said, about 100 of it, but two different resolution, one at 0.15 arc second and one at 0.05 arc second. So we are looking at close to 4-5 AU. So yeah, so let's now look at the new disk images. And yeah, this is the gallery, one of the gallery, and yeah, the scale is 700 AU, and we see, and you can see like very big discs with nice substructures. But I just want to say that not all discs are, if you have seen some, it's conferences or somewhere, you have HL tau was a very Yeah, HL tau is like a benchmark, like everyone in HL tau disk, because it's like a very nice disk. It's like you see the image everywhere, but not all disks are like that. Most of the disk, majority of the observations are this small structured, like non-structured disks, which we are finding right now. And yeah, so this is the 0.15 arcsecond resolution, not yet our best resolution. So, and the subsample, as I said, we are seeing the known disk like Elias 224, where there is a gap. There is a possibility that this gap is not symmetric, probably because of either planets or some flybys. There is a possibility of having some kind of some spiral arms. And yeah, so this is an interesting target. DOR 25 is also like there are some outflows coming out here. Although this is younger disk compared to this one. This is again very interesting because we are seeing substructure both in younger and older disks. So that was something of a dilemma, something of a interesting result.
What is the color?
It's just
Temperature or
no, it's
brightness and frequency?
no, it's just
Brightness.
yeah, it's just the brightness.
So that's the 410 gigahertz flux.
Yeah, would be that.
So, and the color scheme, like center is always bright.
Yes, the central or like the center is not always bright. Like this part is the brightest, and okay, I should have put this color scheme, but it's very so yeah. This is the brightest, and then the green is the less, like the blue is the least brightest, so it's rainbow. Yeah, and this one, for example, is a binary. And if I say that this is the brightest point, and these are noise, so you can imagine how flux limited it is. This part is very like low in flux compared to this region. And yeah, there are this, as I said, like this, and again there is a king here. We are still trying to understand. I can talk about each of the objects for hours. As a class 1 is less than like 1 million year to 2 million year. Yeah, I would say 1 to 1.5 million years. The age is not very well studied. It's still being with Gaia. We are still studying it, but it's 1 to 1.5 million years. And class 2 is 2 to 5 billion years. So yeah, this is the age, which is yeah, the SEDs. That is why I said it's a little old. Like it's observations. The age is determined, so we are still refining that. So I would say 1 to 1.5 because of this, but people will say that less than 1 million year is class 1, but 1.5 is the standard right now. So the beam, when I say 26 AU, so is this. So this is the same measure as this is 26 AU. And that is the resolution. That is like a PSF, you can imagine. Yeah.
Why is the brightness not in the center but in the two sides of the disk?
So this one, so this is what it is in. So there is a central cavity. So there is nothing in between. So that means that the star is, since it's like it's a Fourier transform. So when we do, it's like a Bessel function, right? When we do an inverse Fourier transform, so it's like a Dirac delta, and it gets removed, the central star. So just looking at the continuum, we are not looking at the gas here. So it's just the continuum. That's the idea. If we look at the gas, we will see some observations here, but this is just dust. So that's why this star is like a point source and nothing is seen here. And on the each side there is the dust disk. and it's like inclined. This is the forward side, and this is the back side of the disc. And this is why this is brighter.
That part is like.
Yes, inclined in this way. This is forward. That is the back side of it.
Light is exactly in there.
No, why is there a gap between the front and between the two
central
red
gap.
spots? Yeah, no, between the two red spots,
This part.
there is green, right? Yeah.
Yeah.
Why is that?
So, yeah, ideally it should be symmetric.
Right.
But you can see that here as well. Not all of the discs are symmetric. And this is not an artifact or a data reduction. This is a real effect. And this is a position angle, the position angle, how it is, and it is an ellipse. So it's not a full circle, which is why it's the sides have it's how we are seeing it. It's the plane of axis.
And so this in some two cases, as you said, there is blue at the center, which means that the star or protostar that is not, I mean, that is
There is
subtracted
no
out.
dust.
But what about the top one? So at the center is actually.
Yes, so there
Right.
is, it's not, we are not just seeing we are not seeing the star, but the dust in the disk. So right from the start, so if you imagine the black body, so we are seeing the spectral energy distribution, we are seeing something flat. We are not seeing a dip. If you look at this SED here, there will be a if you look at the radial profile. So if you look at the radial profile, there will be a dip here because there is no dust around it. And this is what we are saying. This is what we call substructure disk, and this is without any substructure. And we understand that there is planet formation here. But obviously, we are not seeing the planet. And if you look at direct imaging also, right now, we don't see the planets because of our limitation. As you recall that we are only seeing Jupiter size, like big major gas giants. There might be some like Earth size or rocky planet formation, which is clearing the dust. Again, this is just images of the dust continuum. This is not gas observation. If you look at the gas, we might see some interaction. In this particular case, we do see interaction. There are papers you can look at, Gonzalez et al. 2021. There are gas observation which clearly shows that there is some interaction between the disk and something around it. So yeah, this is why we see structures and we are seeing some gaps, and this is what we call disk with cavities.
So this dust emission, this is essentially thermal emission.
Not it radio.
What is the radio emission?
It's from the ISIS. I don't remember exactly, but yeah, it's not purely thermal, I would say. Yeah, it says, yeah, it's a thermal emission. So that's why when we look at direct observation, direct imaging with near infrared images, it's very clear. But with ALMA, it's thermal emission. There is a part, but it's radio observation and it's not exactly purely thermal. I don't remember right now. I have to recollect what it is. But yeah, I can write to you to give that answer. That's a great question. So again, let's get into a bit of technicality here. So again, I wanted to just give a disclaimer when I give the next part of the talk. I will talk about this radial profiles. So there are two ways we are getting the radial profile. One from the image directly. So looking at the image plane, we just get this dashed line. But when we look at as I said, the Fourier plane, if we look directly at the Fourier plane, before doing the image reconstruction, and then fit the direct observation, which we see from the Fourier plane. So we have some models which can fit the images, the Fourier plane. We call them visibilities. So the Fourier plane, and then we get more details, something like we get more structures that might be there, but we don't see an image reconstructed image because of power data reduction limitations. So this I will, all the radial profiles I will show are from this fitting of the Fourier plane, for fitting directly done in the Fourier plane, model fitting. And I would strongly suggest to look at this method. It's very nice. It can be used for, I think, galactic model fitting as well, because it's the same principle. It's the same discs.
Now, what is Frankenstein?
Yeah, so Frankenstein is the name of the model. So this is what it's the link. So this that's just the name of the model. It's
So,
yeah.
when you model to get the radial profile.
So as I said, we can directly look at the image, right? We can just simply use the project the image and get the image plane. But when we do image reconstruction, because as I said in interferometry, when ALMA, we are looking, when the detector gets everything in Fourier plane.
Okay, so it's the image processing
Yes.
model, not the model
For the disk.
for the disk.
So the radio, yeah, it's from the ALMA. Yes, instead of clean something.
So is this light polarized or?
Yes. Yes.
Maybe that can tell us about the green stuff.
Yes, it can. So the polarized light, another good point. So I don't have the images here, but yeah. We are looking the polarization. I don't know why, but ALMA, we don't use the polarization so much. So maybe it's hard to reconstruct the images. But polarized observations can be done by sphere on VLT and Gemini both. And in infrared, it's very common to do for particularly observations for like not protoplanetary disk, but debris disk, because in protoplanetary disk, since it's much thicker, the polarization, the total polarization can be skewed. But for there is also gas interactions there. So, but yeah, like, but that's the reason. So for debris disk, it's much easier to do that. So that's that. For that polarization, it's a different instruments you are used, and it's much easier to do polarization with James Webb, with VLT, Gemini. And so yeah, now going to the better resolution images. The most of the discs are different, but there are some common discs between the two resolutions. Like for example, this one is common as the no central cavity. But again, majority of the discs are not very like nice looking discs with substructures, very massive, with signs of planet formation. But yeah, my boss always says that these are very important, because this is where planet formation should start. And our observation is the first time we are not just looking at massive disks like which we had known before, Elias 220, like hundreds of AUs, but also small disks within 10 AU radial distance. So now the planet evolutionary models, which never took into consideration this small disks, this less massive disks, will start taking this into consideration for planet forming models. And I will tell you why it is important. It doesn't follow the norm. So here you can see the previous observation and the current resolutions. You can see how much better we are. Like, this is one of the most I like this disk a lot. So this is SR13. So before we had something very compact we didn't see much structure. We knew about this binary. It is a binary. We knew about this binary, which is not in the same plane, but away. But we also see this central kind of gap, a ring. And then there is some, we hope there is a gap. And then there is further the disk emission is there. So it's an interesting disk, and this is the first time we are seeing these structures. All the ones which are below, we are seeing for the first time. This one again, there is a big discussion between me and Anurup about this. We believe that there are like 3 systems, not just 2. This is 1, 2, and there might be these 2 stars instead of 1 disk. That 2 or 1 star and a possible planet forming, which is this shadow here we are seeing. So, yeah.
For this first 2.
As of 2.
First 50 microsecond things, I don't see that brightness thing.
If you this brightness is not there. This you see the small dot here. This is the brightest part of the ring. If you look at this part, the beam, the PSF is here. It's very small because we can also see the binary much better.
Yeah.
So that's why the resolution. So, and then we can see this bright big blob, which we were not resolving very well. We can see here that it's the brightest speck, like cluster of pixels here. So, but yes, the disk is, I don't know how, like,
Is it laser?
Yeah, it is inclined. No, it is inclined. It is in an inclination.
It is
Because it's like a position angle and inclination. So
It is not an exact angle.
It's not an it's like, yes, it's an ellipse.
it's better here. Look at the better thing is more circular than before.
I would still say it's an ellipse. Yeah. Knowing it is primarily, we believe it's not an artifact, it's a structural difference, and this is because of interaction between, it can be several things. It can, if you don't see a planet there, it can be because of binary interaction, it can be with the ISM interaction, it can be due to capture from something else from another disk, or it can be a flyby. So there are several things. Yes, third party phenomena if we don't see a planet there. Most of the time, all of, like, majority of us, we would argue that it's a sign of planet formation. Any substructure we see is a sign of planet formation, because that's the most obvious answer. Let's look at the obvious things first. And we don't see planet formation because of our limitations of observations. That's the problem. So we hope that with TMT, Nancy Grace, with ELT, we can better resolve. Again, I would say that James Webb was not designed for looking at better resolution, so we should not expect. One thing James Webb is doing very nicely is studying the planet atmosphere, but it will not find us Earth type of planets. So that's just, let's be clear on that. Yeah. So, okay, there are pretty images, but why should we care, right? So does our current planet formation ideas and theories hold? This is one of the questions. And what type of disks are forming what type of planets? So what type of planetary system, what type of disks would form?
So, Tisha,
Yes.
ideally, you have about 5 minutes.
Okay, I'll finish that. So it will be very quick now. So why we are seeing certain planet formation? So before I said HI 8799, which was planets at very far AU distances. And then there is TRAPPIST. So this is like this, the whole TRAPPIST system is within the Mercury's radial distance, like orbital radial distance. So everything what kind of systems are forming, what kind of planetary forming disks are forming what kind of planets, final results, what is it, and where do we, the solar system, come from? So that is the question. So the evolution of massive protoplanetary disk we had studied, and we knew that, okay, there are class 1 disk, and then there are structures forming, like grain growths happen, clearing out some structures here, gaps. And then slowly there are cavities. So more and more grain growth with time, it will clear out and form cavities here. So more and more cavities are forming because of grain growth and planet formation. So with evolution, this is what we saw. But this is the new result. So we have young embedded without structure. So young systems without some structures, more systems, more mature disk without structure, and the bottom panels are all with structures. So the young disks with structures and mature disks with structures. So class 1 disk with structure, class 2 disk with structure, and this is class 1 disk without structure, class 2 disk without structures.
Your system is no planet.
No planet formation, no sense. It's just like a single, this without any, like if you look at the radial profile, it's flat. There is no sign of any significant structure. And we don't essentially see much of it, is the conclusion. And this is for all the low mass disk. It doesn't follow what we were looking at, the high massive protoplanetary disk. It doesn't follow the norm that, okay, we see planet where there should be more embedded without any structure class 1 disk, and there should be class 2 disk should only be with structures. But we are not seeing the same trend here. We are seeing an equal division. So we can see this with, we are doing independent research on our end. So Anurup submitted a paper recently where he studies the disk sizes, and he's also not seeing difference in this disk sizes. So essentially you can see the class 1 and class 2 disks are very similar in cumulative probability also, you can see that. And again, in when we are looking at the images, when we look at the image plane, we are not seeing here the featureless. We see this a lot of structured disks with which are class 1 system, and there is not much division. Two different distribution is not what we are seeing. So this is one of the result. Another result is what is happening with the binaries. Anurup is studying this as well, and he says what we are discussing in this paper is the binary systems are much smaller compared to single star system. So what would be happening is the truncation radius. So basically it's 0.3 times to 0.5 times the orbital separation between the two binaries. The binary disks, each individual disks are even smaller than the radial distance, much smaller. So which suggests that there will be much faster radial drift. If you remember, I spoke about drift, the radial movement of planets. So that starts at a very early stage when gas drag and tidal disruption starts, and with this drift, there will be much faster grain growth. So we know that there are more binary systems. We have been observing more binary systems, and binary systems are one of the fastest. They are resulting in faster grain growth, and probably it increases the like grain growth and planet formation, which reduces a lot of problems with the planet formation theories we currently have. We can talk about it if we have time later. But yeah, one of the roles of pressure pumps are very important here. And start. So pressure pumps are, let this happen when it happens, but it's like you can imagine when gas is very significantly acting with dust particles, it will create like a, you can see that it's this is the horizontal, this is like the disk. You are seeing the disk like this, and this you are seeing the disk like from top. If the disk is like that, you are seeing from top, and you can see this pressure pumps being created. And in the mid plane, you can see this kind of structure being created while there is a radial drift as well. So this kind of structures will trap the grains and aid in planet formation. So this is one of the implications, one of the results we are studying and are trying to say that, okay, pressure bumps are much more essential for what kind of observation we are seeing. So yeah, now, as I said, the initial planet formation like idea which we had, and slowly evolution with time, this it is not following that evolution pattern. And one reason might be that maybe we are not the structured class 1 disk. One reason might be that the classes are not defined properly, and because of age, and as I said, it's an old old data and reduced from the spectral energy distribution. The second is more scientific. I would say that maybe there are planets or planet formation, but since first of all it's very close to the star, we are not able to look at that area. We are not able to resolve them. So we can look at the NGVLA, the and ALMA with better resolution. I should say that all the observation which I showed you, the gallery, it's like 1 or 2 minutes of observation. Each of these are all snapshot observations. So if we, of course, if you remember the first radio observation slides, if you increase it to 60 minutes, it will increase a lot. The resolution will increase a lot. So I will keep my take-home message here while you can read on, and I'll take more questions if you have.
Let me stop the recording.
The idea about for this is